Okay. So, today, 1 second. So, in today's class, we'll talk about microcanonical ensembles in detail. So, we'll first see what is the relation between the macroscopic and the microscopic definition, where statistical mechanics comes in to set a connection between the microscopic description and the macroscopic description. And then how do we define different ensembles? What should be the conditions for defining different kinds of ensembles? And we will mostly concentrate on microcanonical ensemble for today's class. Okay. So to start with, here, so as most of the sessions go, here we will talk about some basic concepts where I'll discuss about these concepts that would be helpful for problem solving. And then as we proceed, we will solve certain questions. And if you guys have any doubt, you can come back and ask. Okay. So talking about the basic concepts, so microscopic and macroscopic descriptions are related. So if I, yeah. So microscopic and macroscopic descriptions are related. So one of the simple examples could be how one can define temperature. So the very basic definition of temperature comes from the fact that it's the mean kinetic energy of the molecules. So that means there is a relation between this macroscopic variable, which is temperature in this case, with the individual kinetic molecules of the present in the system. Similarly, where does pressure come from? Pressure comes from the collisions of the molecules with the surface. So these examples show that there is an inherent connection between the microscopic description and macroscopic variables that describe a system in equilibrium. And so here, this microscopic theory of matter talks about, so if you have to give a microscopic description, if we have n number of particles, they will be moving in this phase space. And so we have to specify their positions and their uh, momentum. And so in this way, at the individual level, we'll be able to define the system. That is the microscopic description. And then, okay, so we have a participant here. Uh, Hi, hello. I'm audible, right?
Yes.
Yes. So here what we are talking about is we would try to come to this concept of ensembles. And for that, first we are talking about how microscopic and macroscopic descriptions are related. So while the microscopic theory deals with all this like the momentum and the position specifications of the individual particles, we know that here on the other side we have this macroscopic description where we define a system by variables like temperature, pressure, and so these are macro variables. But then the question is, how are they connected? So just like temperature is connected to mean kinetic energy, in general, how can we set this connection between these two kinds of definitions? And there comes the statistical mechanics, which tells us how one should take the mean of certain microscopic parameters, or how these microscopic parameters are to be evaluated or averaged out in order to get information about some macro variables. So the question is that how can we derive the equations of states starting from microscopic descriptions? Or how can we obtain the macroscopic parameters from the microscopic details of the constituents? Okay, so now we already know that multiple microstates can correspond to a single macro state. And this concept lies at the heart of this ensemble theory that we will be talking about. So this gives rise to this concept of ensemble. So let us see here that as formulated with thermodynamics, a macro state of an ideal gas in equilibrium can be described by variables like the energy, the temperature, or the pressure. And then the space of macrostates are considerably smaller than the phase space of the microstates. So the microstates, this microstates meaning which, so in order to describe a microstate, we have to specify the position and the momentum of individual molecules constituting the system. So therefore, there must be a large number of microstates that correspond to a single macrostate. Now here, because of this many to one correspondence, what one can do is one can, so this gives rise to this introduction to of the ensemble of microstates. So if we consider n copies of a particular macrostate, each described by different microstates, so which is shown as different points in the phase space. Phase space is defined by the position and the momentum of the individual particles. And so there we can define this phase space density, which is actually the number of representative points in an infinitesimal volume around some point P and Q, where P is the momentum and Q is the position. So this in a way tells us that how many microstates, so corresponding to one particular macrostate, how many microstates are present close to this point in the phase space. Okay, and then one can compute macroscopic variables by doing this ensemble averages, which is done by something like this. So here O is the function, and we can average out over the ensemble by this integration, where rho is this phase space density, and that gives us the ensemble average. So is this concept of ensemble clear to you?
Yes, ma'am.
Yeah, okay. So now another important concept is the Liouville's theorem, which states that the phase space density behaves like an incompressible fluid. So what does this mean? This means that now if we have here P and Q corresponds to one coordinate of momentum and position for a particle. And then, so what it tells us is that if this is the phase space volume around some point P and Q, and then if we leave it to evolve, it would follow the Hamilton's equation and it would evolve, and then it would go to some other point like this at some later time. But then this region or the volume around the phase space, or that means the number of phase space points in this region remains constant. So that means all the pure states, by pure states, we mean the individual microstates originally in the vicinity of PQ are transported to the neighborhood of P prime Q prime, but occupy exactly the same volume. So that means this ratio of dn d tau is this volume, the phase space volume, dn is the number of microstates, and it's left unchanged. So in this way, this phase space density behaves like a incompressible fluid. And it's very important because this gives us very important results. So what it tells us now is that in equilibrium, the phase space density won't change. So d rho dt should be 0. And from here, what we get is that for this to be 0, del rho del t should follow this relation. It's the Poisson bracket. So this refers to that now, in order for this to happen, one of the possible solutions is that at equilibrium, the phase space density should be a function of the Hamilton. Okay, that is given as rho equilibrium is equal to some function of h. This is then easy to verify because if it is a function of h, this would always be 0. So this solution implies that the value of rho is constant on surfaces of constant energy h in phase space. So this is the basic assumption of statistical mechanics. So what we get from here is that now if we consider an isolated system where the energy is constant, so there so that gives rise to this concept of microcanonical ensemble. So ensemble meaning if we group all the microstates that corresponds to one particular energy, because the energy of the system is constant, all members of the ensemble must be located on the surface where h is equal to E, because we know that this phase space density is constant on surfaces of constant energy. This concept is clear? Did I lose you? Hello? Uh, Hello? Okay, I guess I might have lost you. Uh, but okay. So this is an important concept which tells us how phase space density evolves in time and what are the conditions it should have at equilibrium. So now talking about the microcanonical ensemble. So our starting point in thermodynamics is a mechanically and adiabatically isolated system. So in the absence of heat or work input, the internal energy and the generalized coordinates like the volume in case of an hydrostatic system are fixed. So that means we can specify a system by its energy and by its generalized coordinate like its volume and so on. So the corresponding set of mixed microstates then form the microcanonical ensemble. So the concept of equal probability, okay, so this is inherent in this in statistical mechanics, which tells us that now when on the surface, on the hypersurface which corresponds to the same energy, the probability of each microstate will be equal. So from here we get to this expression for the phase space density, which is a constant value on the surface corresponding to the same energy and zero otherwise. So what we get from here is that now if we have this definition of the phase space density, we can use it. So here omega is the number of microstates, and we can use it to find the entropy of the system, and thereby from the entropy we can also find the different thermodynamic parameters, and from there we can also define the state, the equation of state of the system. Okay, so you would first start with the ideal gas. Now here, the first question that we want to answer, and so the concepts that we'll be using in solving this question will be helpful in all the other kinds of question that comes with this kind of ensemble theory. So we start with the ideal gas. So let us consider a system with n molecules of ideal gas in volume V and energy E. And we want to derive the expression for entropy from the microscopic description. Uh, Everything is fine, right? You're following, because I just want to ensure that you are following. Uh,
Hello? Yes.
okay, okay. So we will start with the ideal gas, and here let us see how we proceed. So this example we will try to solve together, and then we'll use these concepts in solving other problems. So the Hamilton for ideal gas, as we all know, is given by the expression here. So here it's p square by 2m, and there are n molecules. So mu runs from 1 to n. And then in 3 dimensions, if we define it in 3 dimensions, it will be from 1 to 3n. Okay. So first what we have to do is we have to define omega. So here this omega defines the volume. Okay. So if we define a volume, with this relation that H is less than equal to E. So that means it covers the entire phase space volume with the energy lying less than equal to E. And what we get from here is that once we find this omega, that is the volume, we can so do a differentiation of that to reach to the hypersurface with the constant energy. So here let's see how to work out this volume. So we know what the Hamilton is, okay? So the Hamilton of the ideal gas does not depend on the coordinates of the particles. So that means we can get this D3 and Q out. So we get the volume out, okay? So it's V to the power n. And now we are only left with this integral. So this is a volume of a 3n dimensional sphere of radius given as root over 2me. Because h less than equal to e explicitly can be written as this. Now, so what we have to do is we have to find the volume of a sphere which has a dimension of 3n and where the radius is given as root over 2me. Okay. So now let us do it for a general case. Let us first calculate VNR for an n-dimensional sphere of radius r. This derivation is very, very important because the end result that we get from this can be used and has to be used in solving all or most of the questions that deals with finding the number of microstates and all the ensemble theory problems. Okay, so here what we first do is when we define a volume. So suppose we have 3n coordinates and then we want to define the volume. And here it's a spherical volume with radius given as r. So we would define the volume as given here. Okay. Now what we can do here is we can substitute and do this substitution while we replace x by y, where yi is given as xi by r. So this is the new variable. So what we then get is this expression for the volume. Okay. And then this last integral has no dependence on r, but it has only dependence on the number of dimensions. So what is the dimension of space that we are working on? Right? So what we can do is then we can replace this as a constant which depends on n, and outside we have this r to the power n. Is this clear till here?
Yes, ma'am.
Yeah. Okay. So now what we then do is this Cn here, if you look closely, is the volume of an n-dimensional unit sphere. So we want to calculate this value. What is this value? Okay, and how does it depend on n? And then we can generalize it according to what is our desired n value. Okay, to find that, we have to use this identity. Okay, this is the identity for Gaussian integrals. And so this tells us that now if we have, this is for one variable x, and then now if we have n variables, this is how this turns out to be. So we will see how this identity is useful. So what we do is now, this is our expression for volume. We already know that, right? In 3n dimensions, this is the expression for volume. And this can also be written as the one given here while we have done the variable transformation from x to y. What this tells us is now, see, if you start with a, think about 3D first. So we can define a volume as integration of dx dy dz. And then when we change to polar coordinates, we can write it as 4 pi r squared dr, right? So similarly, if we want to use this relation, so this looks, because this has dependence on r, and if we want to write the volume element in terms of polar coordinates, what we have to do is we have to differentiate the volume, okay, and then have a dr, which would give us a the volume of a shell, okay, for a particular radius inside, and then with a thickness of dr. So like if we start with a volume of 4 by 3 pi r cube and then we do a derivative, so we get 4 pi r square, and then dr is the thickness of the shell, and that's how we can define the volume element in polar coordinates. Similarly, we start with this volume here, and then we can write this volume element of the shell as given here. What we then do is now we use this expression in the known integral. So we know that this is the value of this is the identity, and we know that this turns out to be pi to the power n by 2. What we do here is we replace this integral as given here, and then we are working on in polar coordinates. So this summation can be written as e to the power minus r square. Okay, so we do something like this, and this is also equal to pi to the power n by 2, because it's just changing the way this is written. Okay, both of them are same. How this is useful now is that using this relation, we can get an expression for Cn. So what we do here is that now we replace r square as x, and we'll see that it gives us a form of the gamma function. And using this relation, we get to this expression for Cn. So that means this is the volume of n-dimensional unit sphere. So in order to find the total volume for a given radius r, we would do it this way. Okay, so this formula for in general for a volume of an n-dimensional sphere of radius r is very, very general and very important. So is this derivation clear to you?
Yes, ma'am.
Yeah, okay. So what we will then do is we'll see how this would be useful in solving the questions later. So now let's come back to the ideal gas problem. We know that, so this is how we are supposed to find the volume, and there it is not dependent on the coordinates. So we get the volume in the position coordinates out, and then it only depends on the momentum. And there we use this relation that we actually have to find the volume of a 3n dimensional space with the radius given as root over 2me. So what we do is we now replace it in the formula that we have just derived. And this is the expression that we get. So if you go back to this expression here, and if you put n as 3n, and if you put the respective value of r as root over 2me, you would get to this expression. Okay, and then we have v to the power n outside, which is coming from the position coordinates, and that gives us the entire volume of the phase space. Okay, now what happens is if we do a differentiation of the phase space, okay, we get to the hypersurface that corresponds to one particular value of energy. And then sigma naught here is the the area on the hypersurface that is taken up by one particular microstate. Okay, so that gives us the number of microstates that are present on the hypersurface corresponding to a particular energy E, right? And then what we can then do is we can use the relation that the entropy is equal to k ln omega, and that gives us this expression, correct? And once we know S, we can use the Stirling's approximation, and then we get to an expression like this. And here we can use our relations, our known thermodynamic relations, in order to find the temperature, the pressure, or the equation of the state. Everything is clear here?
Yes, ma'am.
Yeah, okay. So now one thing we have to note here is that this definition of sigma naught, okay, this, so it can seem that sigma naught in general just signifies the surface element on the energy surface assumed by a single microstate. But then if we take into consideration the uncertainty principle, we would see that it has a significance, it has a physical significance. And so sigma naught can be and should have the magnitude of h to the power 3n. And here when we have defined sigma, which is given as sigma naught to the power 1 by n, where n is the number of molecules, sigma would turn out to be h cube. Okay, so this has a physical significance, the sigma that we're using here. But is this expression for S correct? So what can be problematic here, or do you have an idea, something that we have missed out, or does this look exactly perfect to you, this expression for S? Hi.
That 3 by 2, the addition.
Okay, so what is wrong with this thing here?
It should be multiplied, no? Sorry, and it should be 2 by 3, right?
Um, so it should not be multiplied, because when we break it, like we'll use this relation, and if we, so ln of AB will be ln A plus ln B, and so similarly we'll get to, so this plus will be there, but you are right in the sense that this factor should not be this exactly 3 by 2. But so try to think in the direction that, so what we did is we defined a volume, we found the number of microstates on the hypersurface, and then from there we found the entropy. Okay, but then if you look at the expression for entropy, something is wrong in the fundamental sense. So if you see This is not an extensive quantity. Okay, so if you replace V by V by N, okay, then the entropy should have also reduced to S by N, right? It's an extensive quantity, but that's not going to happen here because we have this term here, right? It's inside the logarithm. So something is wrong with the expression that we see here. Uh, is the problem clear? Like something wrong? What might be wrong? Do you understand why I'm saying that something is wrong in this expression? Uh, did I lose you? Hi. So see what this expression is not entirely correct, and we will see why. It's because one needs to account for the indistinguishability of the molecules. So here, when we were dealing with all of them, we considered that these molecules are distinguishable. But if they're indistinguishable, which can happen because if we have a molecule, if we have a gas of so uh, some number n number of ideal gas molecules, how are they distinguishable? Okay, so they are indistinguishable, and in that case, the number of microstates will be reduced because now, so the concept that we're using is, suppose you have three numbers, right? So you have three balls. So you have one, two, sorry, and three. Okay, so these are like, just take it as three different entities. Now, if all of them are same, then we can have only one combination. That is just one, two, and three. Fine. But then if we have a combination, so if they are distinguishable, then we can arrange them in three factorial ways, right? So it's like 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, and 3, 1, 2, 3, 2, 1. So all the six combinations. So that happens when they are distinguishable. But if they're indistinguishable, then arranging, just changing the positions doesn't make any difference. So we just have three dots, one after the other. So that's just only one arrangement that is possible, right? So that means if we have indistinguishable molecules, our number of microstates are supposed to get reduced, right? So that means what we have to do here is that now when we define the number of microstates, we have to divide by this factor here, 1 by n factorial. And if we do that, what we will see is this expression of S will change. And then we'll see that it is actually an extensive quantity. Okay. So this paradox is called the Gibbs paradox. And from the paradox, we get this 1 by n factorial, which is the Gibbs correction factor. So with the inclusion of the Gibbs correction factor, we get to this expression for the entropy. And now using the Stirling's approximation, we get to this expression for entropy, which has this 5 by 2 factor here. Okay. And here, if you look at, it has V by N and E by N terms. So that means now if we increase the sample space, or if we increase the volume of the factor by, so if you increase the volume or the number of particles, and then because it has this term V by N and E by En in the expression, it would change accordingly. So that means it would be an extensive quantity. Okay. And here sigma is identified as HQ. So this is the correct expression for S. So am I clear till here? Uh, I'll consider that it's clear. So what we get from here is that now for distinguishable particles, we will not add the Gibbs factor, but for indistinguishable particles, we'll add this Gibbs factor. Okay. So while in the questions, we have to be careful about whether we are choosing or whether we are working with distinguishable or indistinguishable particles. And accordingly, this 1 by n factorial should come in. Okay. So now that means our general prescription for calculation of entropy, absolute entropy of a classical system, including the Gibbs correction, would give something like this. So we would find the number of microstates, and then KLN omega will give us the entropy. How do we find the microstates? So what we do is we first find the volume in the phase space divided by this factor here h to the power 3n, which corresponds to the phase space volume for a single microstate. So that is the number of microstates in the volume. Then we differentiate it to get the density of states on the surface of on the hypersurface corresponding to the particular energy E. And then when we multiply it by E, so what we get is the number of microstates. Okay, so this is the general prescription that is to be followed in all the questions that asks us to find the entropy or the other parameters starting from the microscopic description. Clear till here? Okay, so what we now do is we try to solve this question here, which deals with harmonic oscillators. Okay, so we'll use that concept in trying to solve for the harmonic oscillators. So let us calculate the thermodynamic properties for a system of n classical distinguishable harmonic oscillators with frequency omega in the microcanonical ensemble. Right? So here, this is our expression. So this gives us the number of microstates in the entire phase space volume, which is defined by h less than equal to E, and h is given by this expression here. So it's p square by 2m plus half m omega square q square. Okay, and then we have n of n classical distinguishable oscillators. So this is the total uh, energy. So now how do we use it? So what we do here now is we substitute m omega q nu as x nu, and then the equation becomes something like this. So here, if you look at this expression, what we see here is that, so if you look at this expression, what do we have to find here? Okay, so this is just a replacement, and then we get to this expression. So the integral corresponds exactly to the volume of a 2n dimensional sphere of radius root over 2m e, which we have to calculate. So can you tell me what this value should be? So here what we have to use is we have to use that same uh, expression for the volume of an n-dimensional space for a particular value of radius. And then we have to use the radius to consider the radius to be root over 2m e, and then it is an 2n-dimensional sphere. So on putting these values, you would get an expression for the volume or the value for this integral here. So can you tell me what this value should be? So if we look back, this is the this is the formula that we have to use. Okay, so here we have to put, in place of n it will be 2n, and in place of r it will be root over 2me. Okay, And then let's see what we get. So what we then get is an expression like this. Okay. So use this relation and we get to this expression here. So this is the value of this integral here. Okay. Now, once we have get to this value, what we have to do next in order to find the number of microstates on the hypersurface, we have to do a derivative of this thing, right? So because this is in the entire volume, so we have to do a derivative. So now if we do a derivative, so this is just writing it in a more simplified manner. And then if we do a derivative, okay, we get, so on doing a derivative, we get the density of states, right? So now that is given as G of E. So what we can then do is the number of microstates can be given as G into E, and then we can use the Stirling approximation in the formula for the entropy, because for calculating entropy we have to do is equal to K ln omega, right? And from there we would get to this expression for S, right? Now, the thermodynamic properties of the system of n oscillators, as you can see, depends on this typical parameter of E by n h cut omega, okay, which measures the ratio between energy per particle and the typical oscillator energy h cut omega. So this is characteristic for many systems, okay, that the thermodynamic properties depend on this ratio of the total energy and the energy that is characteristic of the system. So in our case, or in this case, it is h cut omega. So now what we do with this expression for S? So if we get to this expression for S, we can find the different other parameters or thermodynamic parameters like temperature or pressure from this expressions, okay? And we can also uh, get the equation of state from this expression. So given S, we have to find the equation of state. So what do? You use the thermodynamic relation that del S del E equal to 1 by T, and then that gives us this expression where we have E is equal to NKT. So this is quite understandable because now what we have is, so it's a one-dimensional harmonic oscillator. So each oscillator will have half kT of kinetic energy and half kT of potential energy. So for each of the oscillators, the total energy is kT. And if we have n such oscillators, then the energy will be nkT. So this is all making sense. And now, how do we find the expression for pressure and heat capacities? So we do del S del V, and from there we get an expression for pressure, okay, and it turns out to be 0. So what does this signify? Why is the pressure 0? And is it making sense? So it's making sense, and this is not very surprising, is because now the oscillators are fixed in space and they have no free motion, so they cannot create pressure, okay? And this is also clear from the fact that you can see the number of microstates or the entropy do not depend on the volume of the container as well. So now this is the expression for pressure, and now you can also find the expression for the specific heat capacities. And you will see that this is the expression that you get. Here, what this tells us is now because pressure is 0, the system does not perform any volume work. And so the specific heat at constant volume and constant pressure have the same value. Okay. So this is how we can derive the expressions for the different thermodynamic parameters or the heat capacities or the equation of state starting from the entropy by first starting with the microscopic description and defining the number of microstates. Okay, so this was for n classical distinguishable harmonic oscillator. So here it's along 1D. Now what happens when we have n harmonic oscillators in 3D? So what will then happen is, So this is your expression now. What has changed? So initially we had, if you look at this expression here, so initially we had this integral from nu equal to 1 to n, but now because it's in 3D, nu will change from 1 to 3n. So similarly, depending on your dimensions that your question or your problem specifies, you have to change your variable numbers accordingly. Okay, so this is your expression for the Hamilton, or this gives us the total energy. Now what we do, we put it back in this expression. Okay, we put it back in the expression for the volume. Okay, and then using the same formula that we have just derived, we would get to this expression for uh, the volume. And then how do we find the microstates, number of microstates? We follow the same procedure. We do a derivative with respect to energy, and then we multiply by E. Okay, and then this on for large n, we can use the Stirling approximation, and there from there we can get back to this expression for the entropy. Okay, even here you can see this E by n parameter that is coming. Okay, so in obtaining this expression, what we have taken into account is that the oscillators are distinguishable. Okay, because as you can see, we don't have this 1 by n factorial term here. So depending on the question, so here if you consider this case where the oscillators are fixed in some lattice or fixed in some position, we can consider them to be distinguishable because they can be distinguished depending on their position on the lattice. But now if they are free moving, or if they're free inside a volume, in that case you have to consider them, or it's more reasonable to consider them as indistinguishable. So depending on your question, you have to choose what your particles would be, and if they are distinguishable, as in this case, you should not include the 1 by n factorial term, and as you can see, we haven't included that term here. And then accordingly, you can get to the expression for temperature, which is just using the thermodynamic relation that del S del E is 1 by n, 1 by T, and that gives you the expression for energy. And here, the average energy per oscillator is 3 kT. So initially it was kT for one dimension, now it's 3 kT. So all of this is making sense, right? So this is how we use our microscopic description and we get to the thermodynamic parameters for harmonic oscillators. Okay, now let us look at this question. Okay, we considered a system of n non-interacting particles, each fixed in position and carrying a magnetic moment mu. Okay, and then it is immersed in a magnetic field H. Each particle may then exist in one of the two energy states equal to 0 or equal to 2 mu h. Okay, we have to treat the particles as distinguishable, and that makes sense because these are fixed in position, so we can distinguish them depending on their position. Okay, so now the question is, find the expression for entropy in terms of the number of particles in the upper state. Okay, that is for the energy E equal to 2 mu h. And then once we find the expression for S, we have to find the value of n, or the number of particles in upper state for which Sn is maximum. And then treating E as continuous, we have to show that the system can have negative absolute temperature. And what do we mean by negative absolute temperature, and why is it making sense in our question here? Okay, so let's try to solve each of the questions one by one. Excuse me. So what we now do here is we have n non-interacting particles. Okay, out of n, let us consider some n1 number of particles which are in the upper state, or let us consider the small n number of particles which are in the upper state. So in order to find the entropy, the first thing that you have to think is how many microstates are possible. How many microstates can correspond to the fact that you have n small n number of particles in the upper state. Okay, how do we get that? So we have total n non-interacting particles. We want to put small n out of them in the upper state. How do we do that? So what we do is the particles are distinguishable, and so in order to find the number of ways, we do nc small n. Okay, so n factorial by small n factorial into n minus n factorial. So these are the number of ways in which one can put small n number of particles out of capital N particles in the upper state. Okay, so once you get that, these are the number of microstates. Okay, now what you have to do is, once you get the number of microstates, you have to now find the entropy. How do you do that? So we just do k ln q, right? So then if we do k ln q, this is your expression for entropy. Simple and clear. Okay, so now once we get the expression for entropy, how do we find the value of n for which Sn is maximum? How to do that? So whenever we have to find such kind of values, what we do is we differentiate S with respect to the parameter and see when it becomes 0, right? And then the double derivative should be less than 0 for it to be a maximum. Okay, so we do that. What do we see is, now this is just rearrangement. So S by K goes as, so here we will be using the Stirling's approximation. And then if we do this derivative, what would then give us is something like this here. Okay, so we set it to 0 because we want to find the maximum value. We want to find the condition or the value of n for which this is 0 or S is maximum. And that gives us that S is maximum when small n is equal to n by 2. Okay, so if you plot Sn versus small n, you'll get a plot like this. Okay, now what this tells us, okay, if you just look at it, this n, this n can be written even in terms of the energy, right? Because so n number of particles in the upper state. So the total energy would turn out to be n into 2 mu h. And from there we can write E, or the energy, in terms of n. So that has a linear dependence. So in a way, this shows how entropy changes with energy as well. Okay. So if you look at the third part, it was that treating energy as continuous, we have to show that the system can have negative absolute temperature. So the very first thing that we have to think is, we have entropy and we want to comment on the temperature. So that means, in a way, if we can do find the sign of the derivative del S del E, that will tell us about the sign of the temperature, right? So if you now look back here, what you can do is that, see, E is equal to N into epsilon. Okay, and so you can write N in terms of energy. There's a linear relation, and what it tells us is that now if you look at this region, del S del E is less than 0 for energy greater than N by 2 epsilon. So for this region, we have this negative slope here. What this tells us again is that now, if we use this relation 1 by T equal to del S del E, we'll see that temperature is negative here for these values. Now, what does this mean? What do you mean by negative temperature, and why is it making sense in this case, or is it always true? What are the situations under which one can get negative temperature? Okay, so the difference, so in general, if you have some number of particles in a box or in a volume, we don't generally have negative temperature. Okay, but what is different from that and this question, that in this question we are getting this region of negative temperature? So if you look closely, the reason that here the energy level of a single particle The reason here is that the energy level of a single particle has an upper limit. Okay, so if you have a gas system, so if you have number of particles fixed, confined in a volume, and then the energy of individual particles does not have an upper limit. So in that cases, the entropy is an increasing function of energy. And there we don't get, because it's an increasing function of energy, we don't get negative slopes and then we don't get negative temperature. But in this case, we can see that for a single particle, the energy level has an upper limit. So in all these kinds of cases where we know the upper limit of energy, okay, for one particle system, and so that would in a way tell you the region where you can get this kind of negative slope, and that is the case where we can get negative temperature. Okay. Okay. Now coming to the fourth question. So the fourth question, okay. So the fourth question is the following. Consider a system composed of a very large number n of distinguishable atoms. So because it's distinguishable, that means we don't have to include the Gibbs correction factor. Okay. And then they are non-moving and mutually non-interacting, and each of which has two non-degenerate energy levels. Okay, 0 and epsilon. So similar to the other, it's the same two-level system. Okay. And then let E by N be the mean energy per atom in the limit of N tending to infinity. So we want to compute entropy per atom as a function of E by N. So that is the mean energy per atom. Okay. So how do we do this? So the first thing that we have to do is we will consider that N1 atoms are in state with energy epsilon. Okay. So what are the ways of putting N1 atoms in energy state epsilon? So we can do it in this way. So n factorial by n1 factorial into n minus n1 factorial. So it's just the different ways of combination, okay? nc n1. And once you have done that, so this gives you the number of microstates that corresponds to the, the macro state where we have n1 atoms in energy state epsilon, okay? But then here the microstates are written in terms of n1. What we have to write is we have to write the number of microstates in terms of E by N. How do we do that? So that means we have to write N E by N or write E in terms of N1. So when we have N1 atoms in states with energy epsilon, we can write the energy as N1 into epsilon. So that is the energy of that state. That means N1 is equal to E by epsilon, right? So what we then do is we put this expression here. We put this expression in the expression for N1. Okay. And what we get? We get something like this. So now this is the expression for the number of microstates in terms of the energy, right? What we will next do is, because we are working with very large number of atoms, we would use the Stirling approximation, and we would use the relation that S is equal to KLN omega. Okay. So if you do that, what you get is the following. Okay. So the entropy of the system is given as KLN, this term. So we now have to simplify this. Okay. So for E by epsilon much greater than 1, or N minus E by epsilon much greater than 1. So this happens when you have this very large number of atoms. And what you see is that now this is what we do is we break this individual terms. So n ln n factorial will be n ln n minus n using the Stirling approximation. Similarly, we break this term and both the denominators, and we get to some expression like this. Okay. So here we have divided s by n. Why have we done that? So we have done that because we want to write in terms of E by N. Okay, so we'll write it in terms of E by N. You can see here all the terms are given as E by N. And even here you can see that the expression is actually, so this tells us that entropy is actually extensive. Okay. So this is how, so that means now if you are asked what is the value of uh, energy for which the entropy is maximum. So you can, what you can do is now you can uh, do a differentiation of this term, of this expression with respect to energy, and then setting the derivative to 0 would give you the condition for the value of energy for which, or the value of mean energy per atom for which the entropy is maximum. Okay. So depending on the terms in the, depending on the question in which terms your entropy is supposed to be written, you can do this kind of substitutions, right? Okay. So next, coming to the next question. So here, the number of microstates of a gas of n particles in a volume V and of internal energy U is given by this expression here. Okay. And so here P is the pressure, V is the volume, and T is the temperature. And we have to find how they are related. So what we have to find is we have to find the equation of state, right? So these are the options. So how do we proceed? How do we proceed with questions like this? Okay. So we know the number of microstates. We have to find the thermodynamic parameters. So the simple way is we will start with omega and we'll find the entropy, right? And once we find the entropy, we can find the temperature, we can find the pressure, and from there we can get an expression for the equation of state, right? Okay. So if this is your expression for the number of microstates, okay, so you do S equal to K ln omega, and this is just taking the logarithm, right? And then we have to use this relation. So this comes from the second law of thermodynamics again, TdS equal to du plus PdV. So that means what it tells us is del S del U is equal to 1 by T and del S del V is equal to P by T. Okay, so from the expression of S, now if you do a derivative with respect to internal energy, what you will get is 1 by T, right? So if you do that, you would get to this expression. Now this is also this in a way is one way of one you can say equation of state, which so it gives us an expression for the internal energy, and then you can do del S del V, and then what will that give you is the that will give you P by T, and then you can replace the expression for T, and then that will give you the expression for pressure. Okay. So now if you do that, you have the expression for T, you have the expression for P. So what do you have to do? You have to see which one matches, right? And then, so what you can see from here is that P into V minus NB is equal to NKBT, and that matches with option D, right? So, so this is your answer for this type of questions. So the most of the questions which comes with this kind of uh, defining a system with a fixed energy. So whenever the system has a fixed energy, you would say that it's in microcanonical ensemble, and using the ensemble theory, you have to start with the number of microstates, find the entropy, find the other parameters in terms of the entropy using thermodynamic relations, and then you can find the equation of state. Okay. So that, so see here D is your answer, right? Okay. So now let us look back at some of the concepts that we have been working on till now. Okay. So in a classical microcanonical ensemble for a system of n interacting particles, the fundamental volume in phase space, which is regarded as equivalent to 1 microstate, will be how much? So how do we do that? Okay, so where have we used this concept? So if you look back, if I go back, you'll see that we have this concept here, right? Or a more better way will be this. So what is the smallest volume that a single state can take in a phase space volume? Okay, single microstate correspond to in a phase space volume. So we know from uncertainty relation that del P del Q is greater than equal to H. Now, if we are in three dimensions, this is expression that we'll get for n number of particles. Okay, if there are n number of particles and we want to describe the system, so describe a microstate, we can, the uncertainty that lies in that is given by this relation here. So the smallest volume that a microstate can take will be h to the power 3n, right? This is for n number of particles in three dimensions, right? So this gives us that expression for sigma naught, and that is the physical significance. So whatever we are doing here is a classical description. We are trying to deal with classical statistical mechanics, but then what, just by using this quantum mechanical concept, we get to this this term which has the inherent quantum uncertainty in defining a system or defining a microstate. Okay, and this is necessary in order to define absolute entropy. So if we go back to the question that has been asked, so here in the classical microcanonical ensemble, the fundamental volume in phase space, which is regarded as equivalent to one microstate, will be A, h to the power 3n. Obviously, we are considering it to be a three-dimensional phase space, right? Okay. Now coming to the next question. In a microcanonical ensemble, a system A of fixed volume is in contact with a large reservoir B. Okay, then which of the following will be true? So this questions in a way is just to get this main concept into our head, that when is microcanonical ensemble, when do we consider a system to be in as a microcanonical ensemble? So in that case, we define a system by its energy, okay, by its energy, or you can define by the generalized coordinates like the volume, okay, and then the number of particles. So what remain fixed here is the energy. Okay, so microcanonical ensemble is for an isolated system, and so the answer here should be that there is no exchange of either energy or particles with the reservoir. We would later see that for a canonical ensemble, there we can have this exchange of energy with the reservoir, and then there what remains fixed is the temperature. Okay, and then that will come in the next class. But so what's important in defining these ensembles is what are the thermodynamic parameters that define the system, right? So for this case, the solution will be the first one. Okay, so the A can exchange neither energy nor particles with B. Okay, okay. Now this question here. So if rho represents the density of phase space, which of the following is the equation for Liouville's theorem? So what does Liouville's theorem tell us is that the phase space density is it evolves like an incompressible fluid. And there, so that means d rho dt should be 0. And from there, if we look back, what we will see is the following. So here, this is the Poisson bracket. And so if we use this relation, what we get is del rho del t plus Poisson bracket of rho h is equal to 0. Okay. And if we remind ourselves that had given us this idea that at equilibrium, or in order to define, so if we have members of an ensemble corresponding to an equilibrium macroscopic state, this can be achieved by this stationary density function. So when we say stationary density, that means del rho del T is 0, and which would imply, so that means it doesn't have any explicit thermal dependent, sorry, time dependence. Okay, and then that means the solution that we get is rho equilibrium is the Poisson bracket with the Hamilton is 0. So that means it's a function of the energy, or rho remains constant on surfaces of constant energy in phase space. So this is the basic assumption which comes from Liouville's theorem. And so one has to remember the expression for Liouville's theorem. So for, if I go back to the question, so if we go back to the question, the expression that would be the solution is the solution 1. Okay, del rho del T plus Poisson bracket of rho H is equal to 0. Okay. The next question is, for a microcanonical ensemble, the phase space density inside a small energy interval remains constant, and outside a region, it is what? So this is pretty simple. So when we are defining this ensemble, what we have said is, so if you remember, the phase space density for microcanonical ensemble is defined as 1 by omega for the hypersurface, and we have just considered a slight uncertainty where we have considered that the energy lies from E to E plus del E, but then outside that region it's always 0, right? So all the members of the ensemble lie on the hypersurface corresponding to fixed energy. So here the answer will be C, which is 0. Okay. Now, the next question is, and this is very important, and so this question, so this type of question can come up quite a number of times. So the density of states, okay, GE, of a single particle in a 3 dimension modeled by microcanonical ensemble depends on energy as, okay. So that means density of states defines how the microstates are distributed on the hypersurface. Okay. And we want to see that for a single particle in 3 dimension, how does it vary with energy? Okay. So how do we do that? So for doing that, we have to go back to the same expression of what is the general expression for the density of states, and we'll see what happens when we have single particle and 3 dimensions, right? So let us go back and check, and then we'll get the solution. So here, when we started with the ideal gas, we saw that omega, which gives us this volume, is given as something like this. Okay, so it's the volume in the phase space, and then when we find, so this is okay, now omega here, which is the number of microstates on the hypersurface, is given by a derivative with respect to energy. Okay, and so this is the general expression for omega. Okay, and this is also, so when we define the density of states, how do we do that? We first define the volume, and then we do a derivative, and that gives us the density of states. So in a way, from here we can see how it depends on energy, and that would tell us how the density of states depends on energy. So here we were working with n ideal gas molecules in 3 dimension. So now we have to think of one ideal gas molecule. So putting n equal to 1, what we see is E varies as half, right? 3 by 2 minus 1. So that means the density of states here in this case varies as E to the power half. Now, what would happen if we have a 2 dimension? Okay, or what would happen if we have one dimension. So what we have to then do is we have to change the number here. Okay, so then we don't have we don't have this 3 here. So the entire expression starts with the same concept that depending on the value of n, we can get the expression for the volume. Okay, and similarly from there we can get to the expression for the density of states. Okay, so for 3 dimensions as given here, for one particle, omega varies as omega, or you can say the density of states in this case, as the question asks, goes as e to the power half. Okay, so for 2 particles, how will that vary? So then we have to put n equal to 2, right? So then it's like 3 minus 1, so it goes as e square. So depending on the number of particles also, the dependence would vary, right? So there can be sorry. So there can be several questions like this which asks about how density of states depend on energy under different conditions. For this case, the answer will be e to the power half. Okay. So these were the general questions that I wanted to discuss regarding microcanonical ensemble. So because we have some time, so what I'll do is I'll go through and we will just recap, and then we will call it a day. So what did we discuss as a whole today? So if I go back, I'll just recap whatever we have done. So we saw how microscopic and macroscopic descriptions can be related. There comes the statistical mechanics. We saw that there can be number of microstates corresponding to single macrostate, and that gives us the concept of ensemble. When do we have microcanonical ensemble? So when the system has fixed energy, okay, it's isolated system, fixed energy, fixed number of particles, then we can define the system, or we can, so all the microstates that correspond to one particular point on the or that corresponding to one energy, then that would define that ensemble of microstates would be defined as a microcanonical ensemble. Okay, the Liouville's theorem tells us how the phase space density evolves in time and space, and it is proven to behave as an incompressible fluid. That gives us how the phase space density should evolve. Okay, and how, what should be the property of the phase space density in order to describe ensembles corresponding to equilibrium macroscopic state. And there the main message is that the density of state should be a function of the Hamilton. Okay, so one such function can be that the density of states is constant, and that's what happens in case of microcanonical ensemble. And there we can see that it goes as 1 over omega over the so along the hypersurface corresponding to the fixed energy, otherwise it's 0. And so from the expression for of the density of states, we can find the entropy, okay, by k ln omega. We get to this expression by considering this, that S is an extensive quantity. Okay, one can also show that this is indeed the most favorable state, because so if we start with S, and then if we consider that there are n number of particles, we distribute it in small phase space volumes, and if we look for the condition when the entropy is maximized, we'll see that for a system with fixed energy, and considering the fact that all states of the same energy are equally probable, we'll get to this expression which says that this is the most favorable, or this is the equilibrium density of states describing a microcanonical ensemble with fixed energy. And so once we have the density of states, we can find the entropy using the relation k ln omega. Okay, and then what we did is we started with this ideal gas, and then we tried to derive the expression for entropy. Okay, what was interesting here is to derive this general expression for n-dimensional sphere, volume of n-dimensional sphere of radius r. And this relation would be useful in all, as you can see in all the in the later questions, we use this formula extensively. So this is a very important formula. So one needs to remember this. And then we used that formula in order to find this the volume. Okay, and then from the volume we do a derivative, we find the number of states. From the number of microstates we find S. Okay, we use the Stirling approximation considering n is very large, and using thermodynamic relations we can find the equation of state, right? And one needs to be careful about whether the particles are distinguishable or indistinguishable. If they are indistinguishable, we have to include the Gibbs correction factor, which is given by 1 by n factorial. Okay, this is what we see here. And then so depending on the question, we can choose whether to put the Gibbs correction factor or not. And as you can see, this is the expression for n molecules of ideal gas. Okay, and this matches with what we just get from thermodynamics, and then we can use it to find the equation of state, right? And so this is the general prescription which we have to follow for different kinds of systems in order to derive the entropy and the thermodynamic parameters. Then with we worked with the harmonic oscillators. First, we did it for n harmonic oscillators in 1D. Okay. And again, here we use that formula, and this is the expression that we get. We see that we have this E by h cut omega, that is quite, so E by n h cut omega that comes up in the expression for S. Okay. And then similarly, we found the different parameters, right? And then we did that for n harmonic oscillators in 3D. And here only what changes is this n here, okay, the summation. So similarly, just the volume changes. So if you remember that formula, all of them comes one after the other. So that's about that question. And then we worked with particles. So general after that, most of the questions were based on 2D system, two level system. So here we worked with n non-interacting particles immersed in magnetic field. Okay, and here we saw that the entropy becomes maximum when we have equal distribution in the two level. Okay, n by 2 and n by 2. So you can, so this is a very general result, and it's better to remember this. And you can see that whenever our the energy distribution or the energy levels are such that the particles have an limit, upper limit to the energy, in that case we can get this regions of negative energy, negative temperature. Okay, which is not otherwise possible in for particles just in a confined in a volume which can have why so which doesn't have an upper limit to energy. And we did similar kind of questions for other 2D problem, two level system problems. Okay, and what is important here, what is important to remember here is that depending on which which is the variable in terms of which you want to write the entropy, you have to do the substitution accordingly. Okay, you can also be asked, suppose you if you were asked to find the value of S, value of energy for which entropy is maximum, you have to do the derivative of this term and see when it becomes zero. Okay, and then this is another question which tells you how you can start with the number of states and then derive the different thermodynamic quantities starting from the number of microstates and finding the entropy. Okay, so there can be numerous questions of this kind, and then we just recapitulated all our concepts. And so this gives us the minimum volume that is taken up by one microstate in 3 dimensions for n particles. Okay, so for one particle it would be h cube. And then this is the basic concept of microcanonical ensemble, that it holds for isolated system where there is no exchange of energy and particle. And we just revised the expression for Liouville's theorem. Uh, we saw that for microcanonical ensemble, the phase density is, is such that the molecules are distributed only on the hypersurface and not outside that region. And this finally we try to see how one can derive the dependence of the density of states on energy and how it depends on the dimensions that we have and the number of particles that we have. So for single particle in 3 dimensions, it goes as e to the power half. Okay, so that's it. Uh, okay, so thank you. So next day we will meet with this concept of canonical ensemble, which is very important because generally we have in nature we have some systems which can be described as canonical ensemble. So in that case we'll see that the temperature there remains constant while we have the freedom of exchanging energy with the reservoir. So in a way you'll see that the canonical ensemble itself is like a microcanonical ensemble considering the reservoir along with the system. So just the system would be a canonical ensemble which has the freedom of exchanging energy, but then the system plus reservoir together would form a microcanonical ensemble where the total energy remains fixed. Okay, and we'll see how we can derive the expression for the phase space density there, and we'll see how we can use the phase space density and derive the different thermodynamic parameters. So that's it for today. Okay, so thank you.